Alright, welcome to this video for Chem 161, where we'll look at some examples for valence shell electron pair repulsion, part of Chapter 5 content. So in our previous video, we looked at things like the definition of steric number, electron geometry, and molecular geometry to help us predict the overall shape of a molecule in 3 dimensions, thinking about identifying electron pairs and moving them away from one another to occupy 3-dimensional space, moving things like planar Lewis structures with 4-fold atoms bonded close together, and moving them at a further angle from the default 90 degrees from one another to now something like 109.5 degrees, and something like the water molecule. We saw that. Okay, so what we'll do here in some examples is build off that. So I invite you to try to pause the video whenever you can to try to check your work and make use of these examples. Okay, so we'll start by working with the name. So we've got to be familiar with our naming rules from Chapter 4 and be able to identify the compound formula and then ultimately describe the correct Lewis structure and then move on to identifying the steric number, electron geometry, and molecular geometry. Okay, so again, pause the video here and begin your work on this example first and resume the video once you have an answer for formula and the overall steric number and electron group geometry and molecular geometry, and also try to draw the correct structure adopting one of the options here. Okay, so hopefully you realized in carbon tetrachloride there's nonmetal, so we're dealing with the material that is CCl4. Okay, that's the formula. The Lewis structure would tell us that we're dealing with 4 times 7. That would be 28 electrons plus 4, so we would have 32 valence electrons to work with for the Lewis structure. We would put the least electronegative element, carbon, in the middle, build up the skeleton, so to have all 4 chlorines around it. In doing so, we've just used up 8 electrons, so we go down to 24 valence electrons remaining, and then we apply lone pairs to the periphery, so we're going to have 2, 2, 2, 6 electrons on each bonded chlorine, and that will use up all 24, and so we now have 0 valence electrons remaining. So the correct Lewis structure is shown here. We can now begin the exercise of identifying electron pairs, so we'll circle them here. So the bonded chlorine at top is 1, 2, 3, and 4. So those are 4 bonded electron pairs at a central carbon. So this must be a steric number of 4. When we now move down into the category for determining the electron pair geometry, we want to consider if there's lone pairs. Well, there are no lone pairs on that central carbon, so we are going to adopt the same molecular geometry and electron geometry for the option there. So when we have 4, we know we are dealing with a tetrahedral electron pair geometry. No lone pairs means we're also dealing with a tetrahedral molecular geometry. And so to show that we're going to end up with a 109.5 degree angle, what we want to do is try to show these appendages now occupying 3-dimensional space. So the best way to do this, we'll draw a central carbon. We'll put 2 of the bonded features in the plane, and we'll show them at a little bit of a wider angle than 90 degrees. So here we're already reflecting 109.5 degrees. And then we're going to show one of these carbons going back behind the page So we use kind of a dashed line for that. And then we'll show one carbon coming out of the page. So we'll use a shaded wedge. Most things that come forward to you are stronger in color. You can even size the chlorine a little bit bigger. And so this again looks like a 4-point jack, or better described, a tetrahedron. And we see now the three-dimensionality where each of these angles is 109.5 degrees. Okay, so that's the carbon tetrachloride example. Okay, moving on, we'll try nitrogen trihydride. So again, this is an opportunity for you to pause the video and try your own work, and then resume the video once you have your work completed. Okay, so the naming for nitrogen trihydride would tell us that we were dealing with NH3, and this would tell us that we're dealing with 5 valence electrons from nitrogen and 1, 2, 3, so a total of 8 valence electrons for a Lewis structure. Nitrogen in the middle, we would apply hydrogens at the 4-point corners of that nitrogen. In doing that, we've just used up 6, so we have 2 valence electrons remaining, and we'll put them on the central nitrogen to satisfy the octet there, and this is the complete and correct Lewis structure. We now need to count electron pairs to help us with the steric number, so we'll identify those here. Electron pairs, we see hydrogen here, hydrogen here, hydrogen here. So there's 1, 2, 3 electron pairs, and there's that lone pair for the 4th. 4 electron pairs here. So this is also, therefore, because we've identified 1, 2, 3, 4, this is also a steric number 4 example, which means that we are dealing with a tetrahedral electron pair geometry. And to determine the molecular geometry, now what I do is consider what the structure would be after having moved all of these electron pairs away from one another and then subsequently ignore the lone pair. So we'll adopt the same ideas as we saw above, move all 4 features away from one another. So we'll put the nitrogen here. We'll put the lone pair at the top. We'll put one hydrogen off on an angle. We'll send one hydrogen to the back. And one hydrogen coming forward. So here you can see that, again, this looks like a tetrahedral, especially if you consider that lone pair. And so this is how we reflect the electron group geometry, keeping the idea of a tetrahedron as the core structure. But now when we think about what the structure would look like without the lone pair, you can see that we are dealing with a 3-point base and a nitrogen at the top. So that is a pyramidal type architecture, and it's a 3-point base. So trigonal planar. Trigonal pyramidal is the terminology there. 3-point base, kind of looks like a pyramid with the apex of that pyramid being the nitrogen. Trigonal pyramidal is the answer there. Okay, we'll try beryllium dichloride next. So please pause the video and attempt this one. Okay, so hopefully your naming helped you identify that for beryllium dichloride we are dealing with BeCl2. Beryllium is in the second column and the second row, in fact. So we are going to get 2 valence electrons from that, plus 7 and 7, so that is going to be 16 valence electrons for this structure. We'll build our skeleton with a beryllium in the middle, put 2 chlorines. We just used 4 valence electrons, 12 to go, to build the rest of the Lewis structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Beryllium is one of these cases that is a very small central atom. We are allowed to break the octet rule and keep it just as is. Trying to make multiple bonds between chlorine and beryllium by borrowing would not be allowed because the chlorine is very electronegative, and that would bring chlorine too close to beryllium since beryllium is so small. So we'll accept this as the best Lewis structure, and this is the correct Lewis structure. Okay, so with that, we can now start to count electron groups. So at the central beryllium, there's an electron group to the right, an electron group to the left, and there are no lone pairs, so this has, therefore, a steric number of 2. When we have a steric number of 2, we have a linear electron geometry. This now lets us consider what the molecular geometry is. So it would simply be these 3 atoms in a straight line with flanking chlorines. We've put 180 degrees between these electron pairs. That is the maximum angle we can have between electron pairs. And so the linear geometry is what puts these repelling electron pairs best away from one another. And because there are no lone pairs to ignore, we also adopt the word linear for the molecular geometry. Okay. Looking at our next example, we have oxygen. So this is O2. We are dealing with 6 times 2, 12 valence electrons. We don't have a central atom because there's only 2 atoms here. So we'll start with just a skeleton there. We've just used 2, so we've got 10 valence electrons to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't have a complete octet on the left oxygen as drawn, so we'll borrow a lone pair, and this becomes this as our Lewis structure, and this is the correct Lewis structure. Okay, next we can evaluate the steric number. Well, we don't have a central atom to look at, so we don't have the opportunity to apply a steric number here, so it's non-applicable. We can still name the electron geometry, the electron group geometry at an oxygen. So we know that there's going to be, basically, no matter how you turn or look at this, the other oxygen is always at a straight line away. So the geometries here are also linear, even though there's no central oxygen atom. So the steric number here is the bit of the exception in this case. Okay, let's next look at sulfur dioxide and try this example. So resume the video when you're ready. So sulfur dioxide, again, non-metal naming, SO2. Oxygen and sulfur are both in the column 6, group 6, so that is, they each provide 6 valence electrons. So we have 6 from oxygen, plus 6 from the other two, 6 from sulfur, and the other 2 each of oxygen each provide an additional 6, so that's a total of 18 valence electrons. For this Lewis structure, start with sulfur in the middle, least electronegative compared to the oxygen, which is higher in the periodic table. So that would be 2 flanking oxygens, just used 4, so we're down to 14 valence electrons now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2 remaining, put them on the central atom, that is sulfur in this case. Examine for octets. We have not yet completed the octet, so we now must consider borrowing an atom, or borrowing a lone pair to complete the octet. And so, as we've covered in previous videos, we're seeing here that there's no right choice between oxygen left or oxygen right for borrowing, and so we have the idea of resonance. So I'm expecting to establish 2 structures to describe the Lewis structure here. So if we start with the idea of borrowing this one, we end up with double bond at left, that's one Lewis structure. That must be in resonance with the double bond at the right. And those would be the Lewis structures that are in resonance with one another, and those are both part of the correct answer. You need them both to report the complete Lewis structure here. We are dealing with 3 features, so we'll look at this now. Trying to count electron groups at the central oxygen. So I see, regardless of which structure I'm looking at, I see 1 electron group here, another electron group here, and 1 at the top. So we've got 1, 2, 3 electron groups on this sulfur. Same thing down below, 1, 2, 3. So this is a steric number of 3. We're in the middle category this time. We have, because we've got a steric number of 3, we're dealing with trigonal planar options for the electron pair geometry. Trigonal planar. And to draw this, what we would try to do next is to push those 3 features equally away from one another. So I'll put the lone pair atop, 1 oxygen at left and another oxygen doubly bonded at right. We know that this angle would be about 360 divided by 3, so that is on the order of 120 degrees. And we could also show this in resonance with the other option. And again, those are the 2 options, both showing trigonal planar geometry. So the lone pair is in the plane with the double bonded oxygen at right and the single bonded oxygen at left. And therefore, after ignoring the lone pair now, you can see that we don't have a trigonal planar molecular geometry. We must have something less. So we're dealing with a scenario here, and the trigonal planar geometry less than lone pair looks like a bent molecule. So that is bent for answer there. Okay, and our last example here is arsenic trifluoride. So again, resume the video when you've had a chance to try this one. Okay, so arsenic trifluoride, AsF3, 21 valence electrons from the fluorine. Arsenic is in the 5th column of the periodic table, so that's 5 valence electrons there. So we've got 26 valence electrons to work with. Arsenic central, fluorine, fluorine, fluorine. Just use 6, we've got 20 to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 2 to go after that, which means we have to put 2 on the central atom to complete the octet. That is the complete Lewis structure and correct one down there. We can now try to identify the steric number by counting how many electron groups we have. So we'll list those here. We see a lone pair atop, so that's 1. Here's a fluorine, that's 2. Bonded fluorine, that's 3. The third bonded fluorine, that's 4. 1, 2, 3, 4. So we are in steric number 4 on this one. Whenever we have steric number 4, our answer for electron group geometry is always tetrahedral. So to draw this, we would put the arsenic in the middle, 1 fluorine atop, 1 on an angle at about 109.5 degrees away. And then we would send 1 fluorine to the back and bring 1 fluorine out of the page here. Oh, I'm sorry, a lone pair at the top. There we go. And our angles below are still the same, still representing 109.5 degrees, roughly, right here. Okay, so looking at that, we've got an AXE scenario, 1 lone pair. So the tetrahedral electron group geometry with 1 lone pair leads to a trigonal pyramidal structure for the molecular geometry. Trigonal pyramidal. Where again, the 3-point base for the fluorines with the apex of the pyramid being the arsenic, trigonal pyramidal. Okay, so hopefully you've been able to follow these examples and understand how we deduced not only the Lewis structure, but worked with that all the way through to determining the electron group geometry, and then ultimately the molecular geometry, looking at things like Lewis structures that were in resonance with each other and still being able to answer the question. And again, moving electron pairs away from one another to try to maximize the angle between